This video covers potential and energy of non-uniform fields. Now, we talked about in our last video that electric potential and electric potential energy are two completely different things. Electric potential is a characteristic of the field only. It is independent of any test charge that may be placed in the field, whereas electric potential energy is a characteristic of the charge field system, and it is due to an interaction between the field and the charge placed in that field. So again, we saw last time that our potential only had to do with the field and the distance, and our electrical potential energy had to do with the charge placed at that potential. So we're going to look a little bit more at electric potential. Again, the difference is the work per unit charge that would have to be done by some force to move a charge from point A to point B in the electric field. And we'll see examples of that in a bit. Again, electric potential is a scalar quantity. So that's really important, meaning that if you want to add potentials, you simply add them. That direction is not important, but here the sign is going to be a really big piece of it. Again, in our last video, we saw that if you move along equipotential lines, then there is no change in potential, no potential difference, or potential difference is zero. So we saw that looking at our picture over here, because my electric field is going down, that means that I have to have a positive charge up on top and a negative charge down at the bottom. These dotted lines represent points of equal potential. So, if an object moves to a place with equal potential, like we saw in our activity, then potential energy does not change and there is no work done. This is something like if you're carrying a mass and you move forward, there is no work done because you have forces that are perpendicular to your distance. Now, I don't want you to write these down, but I do want you to follow along. So, in electricity, we have change in potential. When we move along equipotential lines, or lines of equal potential, then our potential difference is zero. If our potential difference is zero, then so is our potential energy. We have no change in potential energy. And if we had no change in potential energy, then we also had no work done. In our last video, we focused on the potential between two charged plates. So we saw this equation, which was equal to our potential is equal to our electric field times the distance between them. So this equation helped us solve for the potential difference between two charged plates separated by a distance d. Now we're going to look at point charges or spheres. So our equation for this is going to be potential is equal to 1 over 4 pi epsilon naught times the sum, that's what our symbol here means, the sum of all of our charges over all of their distances. Again, this equation for 1 point charge just simplifies down to V equals K times Q over R, where V is potential, K is our constant, which is 9 times 10 to the 9th, Q is charge, and R is distance. So, because potential is not a vector, very important information. Because it is not a vector, what we're going to need to do is add the plus and minus for whatever charge we're dealing with. Other than that, we can just add the way we normally would. So we don't have to worry about vector addition, we don't have to worry about arrows or direction. We just need to make sure that we include the sign of our charges, and we'll see examples of that later. Now, remember that we said positive plates are going to have high potential, and negative plates are going to have low potential. So high, low. So if we're looking at a positive point charge, very, very close to it is going to have very high potential. And as we move further away from it, our potential is going to decrease. Well, if there are no charges in the immediate area, then this is going to decrease until it gets to zero. So here you see that as we move away from it, my potential starts to decrease. Again, let's look at our equation for potential for a point charge. If I put a negative charge, then I have a negative potential. And that potential is going to get more and more negative as we get closer and closer to my negative charge, which we see here. So again, we can say that it's 0, infinitely far away. And then as we get closer to my charge, it's going to approach a higher negative number. In this picture, we have two charges. We have a positive charge and a negative charge. And in green, we have the electric field. So remember that when we have 2-point charges that are next to each other, that some of the electric field lines that go off of my positive charge are going to connect to my negative charge. Okay? And actually, these go all the way out and then back in, if the charges are of the same magnitude. Now, what these gray lines represent are your lines of equipotential. So we call them equipotential lines. And we're actually going to calculate those. So, also what you should notice is that my electric field lines always create perpendicular angles with my lines of equipotential. So, electric field lines. Again, my electric field lines always create 90 degrees with lines of equal potential. So you see 90 degrees here, 90 degrees here. Anytime that my electric field lines cross a line of equipotential, it will be at 90 degrees. So we saw that the 0 point for electric fields and potential is at infinity. So if our distance is infinitely far away, then our electric field will be 0, and so will our potential. But with conductors, charges pile up on the outside surface of the conductor, and this is really important. Therefore, the electric field inside a conductor is 0. However, the potential of a conductor has the same value everywhere in the conductor. And we'll see a graph of that in just a second. This value is equal to the potential at the surface of the conductor. So with the previous slide is, let's say that on the right hand side we're looking at a conducting sphere. So we have two conducting spheres. You can think of our Van de Graaff, the big giant metal ball in class, as a conductor. And this giant conductor has 0 electric field at the very center of it, when a charge is placed on it. So let's say that I put a positive charge on it. Those positive charges are going to be located on the outside surface of the conductor. So there will be no electric field on the inside. If we were to graph that, it would look like this. We would have 0 electric field from the inside all the way until we reach the outer surface. Then our electric field is going to jump up and it's going to match this equation. Remember, Q is charge, R is distance, and K is 9 times 10 to the 9th. And then as we move away from it, it's going to decrease 1 over R squared. Over here, our potential, however, is going to remain constant at all points inside of my sphere. Once we reach the outside of the sphere, then it's going to start to decrease as we move away from it. In this example, we have a non-uniform electric field that is responsible for the equipotential lines shown. So, these lines on the far right-hand side, we have 6 volts, 4 volts, 2 volts, 0, -2, -4, and -6. Now, we're asked to draw the electric field lines connecting A, B, and C. Now, because our points need to be perpendicular, our line needs to be perpendicular to our equipotential lines, then our line is going to look like this red line here. Same thing if we're asked to draw for the electric field lines connecting X, Y, and Z. We also need to make sure that they are perpendicular. Now we're asked to determine the work required to move a 4 coulomb charge from A to B. Remember that work is equal to our negative change in potential energy, which is equal to negative Q times change in V. We have a positive 4 microcoulomb charge, and our change in potential is going to be our potential at B minus our potential at A. So our potential at B is negative 2. Our potential at A is negative 6. So altogether, we get a negative 1.6 times 10 to the negative 5. And because we're asking for work, this is in joules. Here we're asked to solve for the work of taking a 4 microcoulomb charge from B to Y. Well, if B is here and Y is here, they move along the same potential, so the work done is 0. Because the change in potential was 0. So you could have done the whole process. In this example, we're asked to determine the work required to move a 4 coulomb charge, microcoulomb charge from A to Z. Again, A is here, Z is here. So the same work equation. Remember, it's final minus initial. You should get a negative 4.8 times 10 to the negative 5 joules. Here we're asked to see if the charge is released, and we're talking about that 4 microcoulomb charge, is released at Z. Where will it be after moving through a potential difference of 12 volts? So our potential difference of 12 volts is going to get us to position X. Now you might say that our potential difference would actually be a negative value, but all we're really concerned is the difference between. So this is still okay. Now, when we're trying to solve for how fast it's going to be going when it does reach point X, then we can use our Q delta V equals 1/2 mv squared, which is saying that this, which is potential energy, is equal to our kinetic energy. So I can multiply by 2, divide by mass, and then take the square root. Our charge is that 4 microcoulomb charge. Our potential difference is 12 volts. And my mass was 2 times 10 to the negative 6. And you should have gotten a value of 6.93 meters per second. And then our last example, the arrangement is an equilateral triangle with 1 meter long sides. And we're asked to determine the electric potential at point P. Now we said that electric potential is just KQ over R. So when we have multiple charges, it is just KQ1 over R1 plus KQ2 over R2, and so on and so forth, as many charges as we have. The only thing is that you need to make sure that you include the sign of the charges. So that means our potential at point P is K, which is 9 times 10 to the 9th. I'm going to go ahead and pull that out of my fraction. I'm going to go ahead and pull out the R's as well because they are both the same distance away from my point P. And I have Q1 plus Q2. Because we have the same charge and they are opposite in sign, then my potential at point P will actually be 0. Now that doesn't mean that my electric field at that point is 0. It's just talking about my electric potential. and we'll see a couple more examples in class.